Hello, welcome to the next video. And here we're going to look at generating random samples from a Gumbel distribution from using the probability integral transformation technique, or the CDF technique. And this is I think my sixth video dealing with the Gumbel distribution. It started with complementary log-log regression, and there the underlying distribution for the error terms are this Gumbel distribution. And then we went into finding the mean, the variance, the moment generating function, the CDF for a Gumbel distribution, and then we did a video on maximum likelihood estimation of these two parameters in a Gumbel distribution. And then this will probably be the last video over the Gumbel distribution, unless someone requests something in the comments to see about the Gumbel distribution. And the two background videos are probability integral transformation. That deals with looking at the CDF as a uniform 0-1 random variable, and then of course the mean, the variance, moment generating function, CDF of a Gumbel distribution. And we're going to use the CDF in this video. Now we want to compare what we do, I'm going to say from scratch, or with the known Gumbel distribution, and this library has the Gumbel distribution in it, so why create it, recreate it. And here's the density, this crazy looking formula for the density, and the CDF is this exponential of the minus exponential of the minus x minus mu over s, or sigma. And I'm going to refer you back to these background videos if you want more on that. In the probability integral transformation, we learned that the CDF follows a uniform 0-1 random variable. So the technique that we use is we let u, where that's a uniform random 0-1 variable, equal to the CDF, which is this, and then we back solve it for x, and that ends up being how to generate random variables from this Gumbel distribution. And so when we back solve, we get this. So x is equal to this expression, and then where u is the random uniform 0-1 random variable, and then the values we get out follow a Gumbel distribution. So let's generate, what is that, 100,000 random variables from a Gumbel distribution using the inverse CDF technique. Now here we're going to assume that it follows a standard Gumbel distribution. That's where the parameter mu, which is not the mean, and sigma, which is not the variance, is equal to 1. These are just shift and scale parameters. Now what we do is let's plot a histogram of our data, and that's this right here. It's not symmetric, it's skewed to the right. And let's generate the actual density over the top of this, and look how close that is. So our random sample does follow a Gumbel distribution very accurately. Let's change these parameters up a little bit. Let's go 20 mu 0 sigma 22. That's going to stretch that increases the variance quite a bit. I'm curious to see what these look like. So we go from -50 to about 200 or 250, and look how close that still follows a Gumbel distribution. Now I picked 22 at random. I have no clue what that means. And so let's redo it for a mu of 11 and sigma 22. We'll generate the data, plot a histogram, and then draw the actual density of the Gumbel distribution over the top of it. And that follows so closely. And perhaps I probably should have made the line red, and then you can really outline that it's just right over the top of this random sample. Well, that's all I have for today. I think I'm going to jump back into generalized linear model mode, and we'll look at the Poisson distribution or Poisson regression. And well, I hope you enjoyed this video. If you did, please like it and subscribe so you don't miss the next one. Thanks. Bye.